for metals, and they're sort of the simplest case. This is a course called Advanced Geomechanics, so we're really interested in rocks. But of course, the models we're going to use for rocks build on those two models. So that's why I wanted to present those first. Okay. So the first type of model that we might use for a rock would be one called the Drucker-Prager model. So in the Drucker-Prager model, now our yield surface is a function of the pressure and J2, okay? And so we'd have the square root of 3J2, that term would be the same, minus a beta, which is a coefficient, times pressure, minus y. And again, y could be a function of equivalent plastic strain rate, temperature, many other things. Okay, and that's equal to 0. So that's our yield functional. The pressure is, as we've defined it before, it's 1/3 sigma kk. So it's a hydrostatic component of the stress. And, you know, if we use a flow rule and we want to compute partial F, partial sigma ij, if we just look at the term, just look at this term, and we do that computation, then we have partial P, partial sigma ij, which is partial sigma ij times 1/3 sigma kk minus 1/3 sigma kk, and that's equal to minus 1/3 delta ik jk, which is equal to minus 1/3 ij, right? And then should be a beta term there the whole way, right? So this is just to point out that the pressure dependence, there's a pressure dependence in the plastic flow rule. For this model. And so what this model sort of looks like in three-dimensional stress space is it still has a J2 component which defines the end of it, but now this beta, so this line right here that passes through the center of that circle is sigma 1 equals sigma 2 equals sigma 3, right? So that's where I'm at along that line, along the hydrostat, is defined by the pressure. So if I increase the pressure, I move up that line. If I decrease it, I move down that line. Or vice versa, depending on your sign convention. Typically in geomechanics, we use that compression is positive, because in the earth, you always have compressive stresses, so they're always positive. So in geomechanics, we typically use that compression is positive, but in almost every other field, anywhere else, then it's the opposite of that. It's that tension is positive and compression is negative. But the way I've drawn this, or the way I'm about to draw this, is compression positive. Right? So this is positive sigma 1, sigma 2, sigma 3. So anyway, we have the circle the same, and then we have a cone like this. And essentially the angle of this cone is a function of beta. Okay. So if we go along the hydrostat in the tension, then, right, this type of material is sort of like a geomaterial, so it's not going to be very strong in tension. And so, you know, basically, if you're ever out here, you find yourself out here, then it's going to be like instantaneous failure, okay? But as we increase the pressure, as we increase the hydrostatic confinement, then the material actually is going to become stronger, right? So that circle, that cone, it gets bigger. So the region of elastic response of the material gets bigger as a function of pressure. So if I increase the pressure, that gets bigger. So the material becomes stronger with increasing pressure.